All right, so to get us ready for this topic for today, I've got a right triangle on the left, and our angle of interest is right here. So first, draw this triangle, label it with all the symbols and the numbers and everything like that. And we're just going to kind of do a little bit of the opposite from our last lesson, where we're kind of identifying the ratios or the trig function based on the ratios that are given. So I guess what would help is if we label these three sides with opposite, adjacent, and hypotenuse, right? The first one, which side is the hypotenuse? That's always the easiest to identify. What number is the hypotenuse here? Okay, the 10 is the hypotenuse. That's the hype for today, right? It's across from the right angle. It's also the longest side, which we're able to easily tell from this diagram because we're given all three side lengths. What about the 6? Is this 6 adjacent to theta, or is it adjacent or across from theta? Or what did I say? Opposite. Across. It's adjacent, right? It's right next to that theta. So we'd call the 6, this is the adjacent leg, which makes 8 the which side? It's opposite, right? It's opposite from theta. It's all the way across that triangle from that angle theta. And so what I want you to do is something like this. I'm going to give you just a ratio, 8/6, and you tell me which trig function would be represented by that ratio. So for 8/6, I'm looking at this diagram, and I say, okay, 8, that's right here. That's the opposite side. 6, that's there. That's the adjacent side. So I'm thinking opposite over adjacent. Oh, that's tangent, right? TOA, tangent is opposite over adjacent. So I want you to figure out which trig function is represented by each of those other three fractions there. Okay, is it going to be, so 6/10, think about which side over which side, and just write down which trig function it is. Just like 8/6 is tangent, and yeah, that last one's weird, huh? I'm seeing a few stumped faces. Oh, yeah. What is that? That last one. Yeah. Oh, yeah. I wonder what is that? Oh, question mark. Good. Yeah, for that. Yeah. What could it be? I don't know. What's this guy think it is? Oh, okay. All right. What do you think? All right, so 6/10. 6/10, that's adjacent over hypotenuse. What's A/H, everybody? Cosine, right, from SOHCAHTOA. This is the cosine, for sure. So the cosine of theta would be the same thing as 6 divided by 10. What about 8 divided by 10? That is the opposite side divided by the hypotenuse. Which ratio is represented by opposite over hypotenuse? Sine, right? That's the SOH, S-O-H. So this is the sine. And then finally, we've got 10/6. That's the hypotenuse over adjacent. That's going to be the what, everybody? Oh, super duper close. I like the way you're thinking. It's like cosine, but not quite. And so I did see a few students write down the inverse, that -1. But if you recall from our last lesson, the inverse actually doesn't like flip the fraction. It solves for the angle, right? That's an inverse function cancels out a cosine function. So this isn't like canceling out of a cosine. It's close to cosine, right? Because cosine was 10/6. This is 6/10. What's the only difference between these two? Flip it. What do you call that? Yeah, when you flip a fraction. That's a reciprocal. So if this is cosine, or what if I wrote it like this? If this fraction is cosine over 1, 10/6 would be, yeah, 1 over cosine. It's the reciprocal. And if any of you noticed the name of today's lesson or looked on the board, you'd see that we're learning reciprocal trigonometry today. Dun, 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 dun. There's a student in my 8th hour class who always like peeks at the title up here. Like they read the name of my save file in the upper left corner. They're like, oh, 9.0b, good, reciprocal trig, because like she likes to label her notes with the right number or whatever. So she always cheats and looks ahead. It's fine. It's not really cheating. It's always right there on the board. All right. So yes, today we're going to learn about these reciprocal trig functions when you just flip the fraction upside down. All right. So this is lesson 9.0b. We're learning reciprocal trig and SRT. That stands for special right triangles. That's actually a review concept from geometry, but I want to go over those again. But the new concept for today are these reciprocal trig functions. Each of those three primary trig functions, sine, cosine, and tangent, have a reciprocal function, like we saw in that warm-up, 1 over cosine. But instead of writing it as 1 over cosine, it actually has its own special name. Each of the three trig functions, when you take the reciprocal of it, when you basically just flip that fraction, it has its own special name. And all it's doing, each of these reciprocal trig functions, you know, like SOHCAHTOA, like S is O over H. Well, the reciprocal of sine would be H over O. You're literally just flipping that fraction of which side is being, written over which other sign. So go ahead and make sure you've got these three ratios jotted down in your notebook. You know, because you might not remember them since it's brand new. Maybe. And yeah, it's CSC, SEC, COT. What on earth do those stand for? So they're the reciprocal of sine, 1 over sine, CSC. This is actually called the cosecant. So CSC, cosecant. I'll move that up. Cosecant. Any guess as to what 1 over cosine is? Just the secant. So you might have noticed that these first two, they're kind of similar with their naming. If you think about sine and cosine, aren't those almost the same word? Just one of them has co in front of it. The reciprocals are the same way. Secant and cosecant. Right? So these four are very similar. One of them just has the co, one of them doesn't. And it's interesting because like the non-co version of them starts with an S. Sine versus secant. And the way that I always keep these first four straight is that the reciprocal always starts with the opposite letter. So like the reciprocal of sine, which starts with an S, is cosecant, which starts with the co. The reciprocal of cosine, well, since that starts with a C, is secant, because it starts with an S. When you take the reciprocal, it also like flips the first letter. It's just how I always keep it straight. The last one, 1 over tangent, is COT. Want to take a guess as to what COT stands for? Tangent and cotangent. Nice and easy. I didn't hear you. Tangent and cotangent. So tangent, it's just put a co in front of it, and that's COT for cotangent. So as far as these ratios, do you remember? Let's think back to SOHCAHTOA. If sine Let's see, that was SOH. So if sine was opposite over hypotenuse, what do you think cosecant is? Which side over which side? Yeah, you take the fraction of sine, which was opposite over hypotenuse, and you flip it. So cosecant equals the hypotenuse divided by the opposite. It's still a ratio, still a fraction. It's just the reciprocal of it. You're just swapping the numerator with the denominator. Secant is the reciprocal of cosine. Now cosine, let's see, that was C-A-H, ka, right, for so, ka, toa. And if cosine was adjacent over hypotenuse, what do you think secant's going to be? Hypotenuse over adjacent. You just switch them. So it's the hypotenuse length divided by the adjacent side. And finally, tangent, toa, T-O-A. The tangent ratio is the opposite side divided by the adjacent. So what would the cotangents ratio be? Perfect. Yeah, that's the adjacent side divided by the opposite side. So now we do have a trig ratio for every possible combination of those three sides on a triangle. Any two sides in any order has its own specific name. Now, how do you keep this straight? Well, I always start with SOHCAHTOA and then take the reciprocals, but it is kind of nice having that SOHCAHTOA mnemonic device, right? Unfortunately, there is no official way to remember these with a clever phrase, and no textbook or no other math teacher will ever tell you that. But of course, me being the rebellious math teacher that I am, I think it's fun to make a silly little rhyming name, but don't tell any other math teachers that I said this because they will laugh at you and then laugh at me. All right. But if we did make a little phrase to remember each of these ratios, well, instead of SOHCAHTOA, I give you, this is so stupid, I give you CHOSHAKAL. CHOSHAKAL is stupid. Do not use this. It doesn't work. It doesn't. I mean, the reason it doesn't work is because look, there's two C's, right? It's like, oh, is that cosecant or cotangent? Yeah, but technically, so that's CHOSHAKAL. Oh, for cotangent, C-O-T. CHOSHAKAL. Oh my gosh, this is getting worse and worse. Let's stop right now. If you want to use CHOSHAKAL, by all means, try it. I mean, it's... But I'm begging you, please do not tell any other math teachers that Wojcik taught me CHOSHAKAL today. Like, they'd probably start tripping me in the hallways or something, or shoving me into a locker. Like, it would be bad. Just don't. Just do me a favor. It's CHOSHAKAL. It's fun to say, though, isn't it? CHOSHAKAL. No. Wouldn't work. All right, so grab your calculators out, everybody. And we're just going to calculate some of these reciprocal trig values. So once your calculator's out, and these are going to be decimals, right? They're just different ratios or whatever. So to calculate like the secant of 30, go ahead and just press the secant button and then 30 and then hit enter. Yeah, just hit the secant button on your calculator, right? There's the secant button. No, there's no secant button? Huh. Weird. So there's no secant button on your calculator. So how do you think we could type this into your calculator? I like what I heard. Secant is the reciprocal of what? Take a look at your notes. What was it the reciprocal of? It was cosine. The reciprocal just means you just flip the fraction. So if this is secant of 30 over 1, which fraction could we type in our calculator? Yeah, this is the same thing as 1 over the cosine of 30. Can we type that into our calculator? 1 divided by the cosine of 30? For sure. And what do you get? 1.15. Anyone else get that? Here, I'll bring up my calculator just in case. But yeah, 1.15. So that would actually be what the secant of 30 is. Is it 1.5? Thank you. All right, so now go ahead and calculate the cotangent of 45, everybody, and the cosecant of 15. Yes, sir? Oh, yeah. Different calculators. Yep, let's take a look. So do 1 divided by, and then for the cosine of 30, you type 30 first, and then hit cosine. Enter. There you go, 1.15. You're welcome. Any other calculator questions? Making sure you can get that 1.15 for the first one. After spring break.
Actually?
Yeah.
So I can change the mode of my calculator again?
You will. You have to be careful. You have to keep on switching back and forth.
That's kind of messed up. So I'm going to get into physics and it's all really wrong.
Well, it's just like in most science classes, you deal with different units of length. We have an English system and the metric system, right? Meters and feet and inches. So we're already converting a lot. 1 divided by cosine of 30. There's that 1.15. Cotangent of 45. So you type 1 divided by the tangent of 45 because we don't have a cotangent button. 1. Anyone else get 1 for that? That's kind of cool. It's exactly 1. Isn't it nice when you don't have a decimal? It's beautiful. Brilliant. Yeah, the last one, cosecant. And the way I always keep that straight is since this starts with a C, its reciprocal then would start with an S. It always like switches that first letter with the C's and the S's. And so that's cosecant, then its reciprocal is 1 over sine. 1 divided by the sine of, was it 50?
No, 15.
That's awkward. 15. 3.86. All right, so that's what you should have typed in to your calculator, everybody, and gotten those same decimals. And hey, what if you got completely different numbers, but your calculations look exactly like mine? What do you think is wrong with your calculator?
Wrong mode.
The mode, right? Radians versus degrees. What mode should our calculators all be in right now?
From this angle, it should be in
Degrees. And so if it's not, you press mode. Drop down to this third option. You have a radian or a degree. Just make sure degree is highlighted. Press enter, and you're good to go. All right. So those are the reciprocal trig functions. This was, whoops, let me get a pen. This was exactly 1, and this was 3.86. Any questions on these reciprocal trig functions? Oh, good question. Anyone know why I use squiggly lines instead of those straight lines? It means approximately equal to. Because we rounded our answer, it's not exactly 3.86, whereas the cotangent, that's exactly equal to 1, so I use the equal sign. When I round it, I try to use the squiggle sign. I don't always, but in general, just to show you that, hey, the cosecant of 15, it's not equal to exactly 3.86, but it's really close. So for all our intents and purposes, it's practically 3.86. Good question. All right, go ahead and draw this triangle. And I simply want you to identify the correct ratios, meaning like which side over what side. So you're just going to draw like a fraction here, and you're just going to put the correct number on the right spot of that, between the 5, the 12, and the 13. And so I want you to think about which one of these is the reciprocal of, And yes, if you'd like to use Choshikao, you can use Choshikao here. So just identify the ratios. And so when I say ratios, I just mean what's that fraction? It's a poor looking fraction. So just identify those three fractions, those three ratios for those trig functions. I hope so. Could be.
I know that's what it is.
I don't know. Might be. Might not be.
I chose Chicago.
So funny. Is that what you use in your head?
No.
Choshikao?
No.
All right, did we get our ratios? Cotangent. So if tangent is the adjacent over the, no, tangent is opposite over adjacent, then cotangent is adjacent over opposite. Now, I guess the first thing that I would do when I see this triangle is label them A, O, and H for the adjacent, opposite, and hypotenuse. And our angle's down here now, right? That's where theta is. So the 13 is still the hypotenuse, no matter which of the other two angles we're talking about. But now the 5, is the 5 the opposite or the adjacent? It's opposite because it's on the opposite side of the triangle. So this is now O, and that just leaves the adjacent side as the 12. All right, so now I've got them labeled. It's going to be really easy for me to write out these ratios, these fractions. And cotangent is going to be Choshikao. Okay, so that's adjacent over opposite. 12 over 5. Anyone else got 12 over 5 for cotangent? All right, all right. Secant is the reciprocal of cosine. And so if cosine was adjacent over hypotenuse, this is hypotenuse over adjacent. And so that's 13 over the adjacent side of 12. Anybody get secant? Yeah. Finally, cosecant is the reciprocal of sine. Sine was opposite over hypotenuse, so cosecant is hypotenuse over opposite. 13 over 5. Anybody get all three of those? All right. That's fantastic. Nice job, class. So those are your reciprocal trig functions. What do you think? Is this crazy difficult? No, it's just new names for new relationships between sides on a triangle. Nothing intense. Oh boy. This one's going to take a little bit of thinking, but you've already seen this last year. So I'm going to just refresh your memory and hopefully it'll kick in some of these properties from before. So there are two right triangles that are very common. And so they have special names, just like logarithms. Remember how there were two very special logarithms, like your base 10 and your base e? And they had their own special names because they were used quite often in mathematics. Well, same thing with these two types of special right triangles. A 45, 45, 90 and a 30, 60, 90. Hey, why are they named those? Why are they called those different? random numbers. Those are the three angles inside the triangle. 45, 45, 90 versus a 30, 60, 90. And based on those triangles, we have these different relationships for the side lengths. Meaning if I know one side of any of those two types of triangles, I can easily identify the other side lengths by like basically taking a shortcut. I don't have to use the whole Pythagorean theorem, or I don't need to use some SOHCAHTOA or things like that. I can easily look at that side of the triangle and be like, oh, the other side's this and that, which is pretty convenient. It's a big time saver. You know, on something like, I don't know, the ACT, where time is kind of important on the math section, isn't it? And if you know these relationships, you can easily just answer, oh, the other side is that, and then move on within a few seconds, as opposed to taking maybe a minute to work it out with the Pythagorean theorem or one of your trig ratios. So the 45, 45, 90 triangle. First off, if I look at the diagram itself, I see this symbol here that we know that means 90 degrees. But the other two angles aren't labeled 45 degrees. But I know for a fact that they are. I know that those other two angles are definitely 45 degrees. How do I know that, though? That single arc and this single arc, if multiple angles have the same number of those little like arcs or whatever, it means that they are congruent. They're the same length. And since those two angles are the same length, we're going to use that concept along with the idea that all three angles in a triangle must add up to 180. Therefore, if one angle is 90, that means those other two angles also would have to add up to 90, because 90 plus 90 is 180. And so if I have two angles that add to 180, and they both have to be the same, essentially just take 90 and divide it by 2. And what you're left with is a 45-degree angle and a 45-degree angle. So if you have a right triangle with just those two congruent marks, we know that they're going to be 45 degrees each, because they have to be the same, and they all have to add up to 180, and that's the only possible measure that those two angles could be. Now, these side lengths, x, and x root 2. Now, x is just going to be any number. All right, so if this side is, let's say, 12, what's the other leg's length going to be, everybody? The same thing. That's pretty nice and easy. Now, the reason those two are the same is because these angles are both the same, and so the side that's across from those angles would also have to be congruent. If you've got two congruent angles, you're also going to have two congruent sides. Hey, what do you call a triangle with two congruent sides? Isosceles. Do you remember that? Isosceles triangles? Oh my gosh. I know you're all worried like, all right, Wojcik, when's the proofs coming in? Give me some side angle side or... No, not going to happen. Not going to happen. Don't worry. Where are the alternate interior angles, Wojcik? Not this year. Not this year, I promise.
Not any year.
Maybe next year. All right, so those two are 12. Then if I know the two legs are 12, then this hypotenuse, it's just x, or whatever that one leg length is, times the square root of 2. So for my example here with the 12s, I would say that the hypotenuse is simply 12 root 2. Like, I don't even have to do a calculation. It's just 12 times the square root of 2. Now, I could multiply that out, but it would be some irrational decimal because the square root of 2 is irrational. And so we always like our exact values. So just leave it like that. The hypotenuse, it's 12 root 2. Is 12 root 2 going to be bigger than just 12? If I did multiply this out, 12 times the square root of 2, would I get a number bigger than 12? For sure, because isn't the square root of 2, it's a decimal, but it's more than 1, right? And so it is going to make the 12 a little bit bigger. And that goes along with the hypotenuse having to be the longest side on a triangle. Okay, so what about this 30, 60, 90 triangle? Well, wait a minute. I only see two angle measures, the 90-degree right angle symbol and the 60-degree symbol. How do I know that that angle is 30? What if it's something else?
It can't be.
Good. Yeah, all three angles have to add up to 180. That's true for all triangles. And so that's the triangle sum theorem. And then if you have a 90 and a 60, well, then that last angle has to be a 30. And notice when I marked it with those arcs, I put two arcs instead of just one because they're not congruent. They're different lengths, right? 60 and 30 are different numbers, believe it or not. We're learning so much today. So this is a 30, 60, 90 triangle. And since the three angles are different, we're going to have three different side lengths. And the best way to kind of remember these is, well, we all know what the hypotenuse is. That's the longest side. But then you've got two legs, and the legs are different. The way I differentiate them is I call them the short leg and the long leg because one is shorter and one is longer. And the way you identify the short leg versus the long leg is by looking, so this is the short leg, is by looking not just at the diagram, because remember how I said diagrams can be deceptive. You can't trust the drawing and say, well, that side looks shorter, so it's the short leg. Instead, what you should do is look at the angle that it's across from. Since this 30-degree angle is smaller, it's going to have a smaller side across from it. The 60 degrees is a bigger angle, so it's going to have a bigger side across from it. Think of like the opening of a door. If you look at like the hinge of a door, if the door's hinge is only open a small amount, there's only a small opening in that doorway to walk through. But if that opening, that hinge is open a lot wider, isn't the doorway going to be wider for you to walk through, like to fit in? Same kind of idea. So then the side that's across from the 60-degree angle, I'm going to call the long leg. Very technical names, I know. Short leg and long leg. And then you still got the hypotenuse as always. So once you have those sides identified, how do these different lengths relate to each other? Well, for a 30, 60, 90, we want to first identify the short leg because the other two sides are both based off of the short leg because that's just x by itself. You'll notice that the other two both have an x in them, but we need to know what x is first. So if you have the short leg, if that's the side given to you, then it's going to be super easy. The hypotenuse is simply 2 times the short leg length. So if the short leg is, let's say, 8, how long would the hypotenuse be? What's 8 times 2? Just 16. You just double the short leg and you get the hypotenuse. Very easy. Now for the long leg, what we're going to do is take that short leg again, x, which is 8 in my example here, and you just multiply it by root 3. But you don't actually multiply it together. You're simply going to write it as 8 root 3. Oh, that's an 8. They're both really curvy. Come on, it's an honest mistake. Have you ever made a mistake yet this year? Oh my gosh, the number of students who were shaking their heads. No, I have not, Wojcik. Impressive. So then that long leg would simply be 8 root 3. Now you could actually multiply 8 times the square root of 3, but it's going to be some irrational decimal that goes on forever. And so we prefer to have this exact value, which is also less work for you. So that's a good thing. It's less number crunching. So that's how all those sides are related. Now let's try applying them. Solve for the unknown lengths. So solve for x, solve for y. This is example 3. Go ahead and draw this diagram in your notebook and label the sides accordingly. And don't forget to draw any symbols you see on the triangle as well. Those are relevant to help you solve this problem. Because there's this right angle symbol And then these other two angles have congruent symbols. That's very important to help you solve for those unknown side lengths. Let's see if you can do it. It's pretty quick. Look at those calculations. Which letter? Really? No, it's not the 23rd letter. It's the 24th letter. Z is 26, Y is 25, X is 24. Holy cow. Like your alphabet, if X is 22 and 23, 20, what are the last two letters after Z? River and Slim? W, X, Y, and Z, and River and Slim. That sounds like a crazy alphabet. Okay, everybody. So first thing I would do is identify which type of right triangle is this, 30, 60, 90 or 45, 45, 90? How do we know it's a 45, 45, 90, everybody? Two congruent angles. So first say, hey, this is a 45, 45, 90. Now I know that a 45, 45, 90, the two legs are congruent because it's an isosceles triangle. If you've got two congruent angles, we've got two congruent sides. The legs, I know, always make the right angle. They are the two sides that make the right angle. Therefore, since that leg on the left is 13, what does X have to also be? 13. Yes, correct. Good job. They're congruent. They're the same length. No calculation needed. It's pretty groovy. Now I could use like tangent of 45 equals X over 13 and then use my calculator, but blah, blah, blah. What? It's just 13. It's a lot quicker, right? Super fast. That's why it's nice to know these. Finally, Y is the hypotenuse. And if you recall, the hypotenuse on a 45, 45, 90 is just that same short leg length, 13 times the square root of what? Of 2. That's right. Now, the one thing students sometimes will mix up with these two types of special right triangles is, here, let me go back to that previous slide, is both of them have a side that's got a root in it, right? But one's a square root of 2, one's a square root of 3. And a lot of times I see students mixing up, do I use the root 2 or the root 3 for this? Best way to keep it straight is the 45, 45, 90 has how many sides that are the same length? 2. 2 congruent angles, 2 congruent sides. It's an isosceles triangle. It got 2. There's a lot of 2's there, right? Therefore, it uses root 2 because there's 2 congruent sides and angles. The 30, 60, 90, well, what's special about the numbers 3, 6, and 9? What are they all divisible up by? They're all divisible by 3. They're all multiples of 3. And guess what? It uses the root 3. All right, that's a great way to keep those two straight for which one to use root 2 and which one uses a root 3. So because I knew this was 45, 45, 90, I see, oh, there's 2 of the same. I'm going to use a root 2 in that one. Hopefully that helps you keep it straight as well. All right, solve for the unknown lengths, X and Y. Remember, you can't trust your eyes as to which one is the short leg or the long leg. Or are they the same? Ooh. Identify the type of triangle. Identify which side is given to you. And then based on that, figure out what those other sides would have to be. And those of you at home, webcams should be on and facing you. I know, it's crazy. It's like a new policy. Thank you so much. Did you guys finish already? Who finished first?
I did. It's not select.
Do you guys like finish and then like look up at each other and then whoever's eyes?
And I was waiting.
Oh.
Still looking at whatever he says.
That's a gracious winner right there.
Select. Still all these notes there, but it's not important.
Nice. Oh, that doesn't. I like, yeah, the 306090 demo in the upper right. It's pretty spot on. Cool. All right, solve for the unknown lengths. Let's take a look. First, identify the type of triangle. I see one 30-degree angle, so right away I know this must be a 30-60-90 because there's a 30, there's a 90. Then this last angle has to be a 60-degree angle. It's got to be. So now the 40 that's given, which side is that? Is that short leg, long leg, or hypotenuse? It's the hypotenuse because it's across from the right angle. So that's got to be the hypotenuse. And if you have the hypotenuse, then the next side that you're going to want to find is the short leg. And that's true for all 30-60-90s, is if you're given the hypotenuse or the long leg first, you always want to figure out what the short leg is because that short leg tells you what the other one is. Like I couldn't go from hypotenuse right to the long leg because I need the short leg to figure out what the long leg is. So then I know that the hypotenuse is twice the short leg. So then if 40 is 2 times y, what does y have to be? 20. You just would divide then, right? If the hypotenuse is twice the short leg is half of the hypotenuse. Just divide it by 2 if you're going from the hypotenuse down to the short leg. And then finally, now that I have the short leg, I can easily identify the length of the long leg. I take that short leg length, which is a 20, and what am I multiplying this by? Just a root 3. Just like that, no calculation necessary. I know it's a 3 because 30-60-90, 369, those are multiples of 3. And that's it, you're done. You've identified the other side lengths. Hopefully very quickly. Faster than River, that's for sure. All right, example 5, find the unknown lengths. Numbers won't always be as nice, so we want to do a little manipulation with radicals. See what you can figure out. So identify the type of triangle. Here, I'll move this up for everybody, if that's easier to see. Identify the type of triangle, and then try to determine those other lengths. Nice, simplified it first, very good. If it makes it easier, you can simplify that radical first. Ooh, which I've seen several students do already. He's not done. Oh, so you don't even draw out the diagram? How's it going to help you, like, review or study or practice or do your homework?
I don't need the diagram.
But are you going to remember this a month from now?
Probably.
Really?
A very good memory. Like Slim.
Looks like Slim's got a lot of notes, and if he forgets 2 weeks from now what he did, he can refer to his notebook and see exactly how he solved these problems, which is the responsible
Yeah, we're
proper thing to do for an Algebra 2 student. That right there, that's a winner. And River, if you're not a winner, you must be a
winner.
Oh, the second winner, the runner-up. So just a little sidebar, everybody. If you've got 8 root 27 for one side of this triangle, we could simplify that radical first, because the square root of 27 can be broken down to the square root of 9, square root of 3. And the square root of 9 is 3, so that's the same as 3 root 3. But then remember, there's still this 8 out in front, so you'd multiply it with that 3 that kind of escaped the radical. And so this is actually the same as 24 root 3. Did you have that?
Yeah. Without the diagram too. Yeah.
This is a 30, 60, 90 triangle. So this side right here, the 8 root 27, or if you simplified it to 24 root 3. By the way, if you still use 8 root 27, you can still get the correct answers. You just will have more simplifying to do later on. Is that the short leg, the long leg, or the hypotenuse?
Short leg.
Short leg, good. It's across from the 30-degree angle, the smaller angle, therefore it is the shorter leg. If I have the short leg, then first I'm going to find the hypotenuse, because it's simply 2 times that amount. So it's 2 times 24 root 3. Now, whenever I'm multiplying, do I multiply both the coefficient and the radical by 2? Or do I just multiply one of those by 2? Just the coefficient, just the number in front. So y is going to be 48, but still root 3s. It's like if I had 24 root 3s and I doubled that, I'd now have 48 root 3s.
Isn't that technically all one number?
Yeah, it's being multiplied together. And so you wouldn't multiply it times other things. It's not like there's multiple terms that you're distributing it to.
Okay.
All right. If you use the 8 root 27, you would double it and you'd get 16 root 27. And then if you simplify the root 27, you'd get a 3 out there, and 16 times 3 is 48. You'd get the exact same thing. Now for the x, though, that's the long leg up at the top. River, what'd you get for this?
The long one?
Yeah. 72? Oh, that's right. It's nuts. Good thing you had your calculator out to help you. So for the long leg, you simply take the short leg length, so 24 root 3, and you multiply it by another root 3. Remember, you take that short leg and you multiply it by a square root of 3. Now I've got a root 3 times a root 3. I can multiply those together. And what is any radical times itself? What happens? It becomes that number, the radicand, right? The roots would cancel out. The square root of 3 times the square root of 3 is just a 3. So this is the same as 24 times 3, because root 3 times root 3 is just 3. 24 times 3 is 72. And so that is x. If we used this 8 root 27, we multiply it by a square root of 3. 27 times 3 is 81. So you'd have 8 times the square root of 81. And hey, what is the square root of 81, everybody? It's a perfect square, right? Square root of 81 is 9. So you'd have 8 times 9, which is, of course, still 72. So you get the same answer no matter how you simplify or when you simplify. You'll get the exact same thing. How many of you got that 72 for the long leg, just out of curiosity? All right. Nice. So yeah, we do have some work with roots or radicals. And now for the tricky one. So it's a bit more of a puzzle, but you can, if you think about it, I bet you could figure it out. I'm sorry. Oh, look who's writing stuff out. That's good. That's good. Now remember, we never want to leave a radical in the denominator, though. No, keep going. Rationalize the denominator. Do not leave a root in the denominator. It is. Okay. So if you went from here to there, normally you take a leg and you multiply it by a square root of 2. So is this times square root of 2 equal to that? Oh, so close, man. Normally, if we had a short leg, we would simply multiply it by root 2 to get this, right? To go from the smaller side to the longer side. If you're going from a bigger side to a smaller number, what operation should we do instead? Yeah. Yes. Yes. And then just simplify those two coefficients, and that'll be it. It's perfect. Yes, sir. Still working on it? So since normally, yeah, you got this right. This, you could set up like a mini equation. You know that this number has to be whatever x is times root 2. So set up an equation, say x root 2 equals 12. Like write it off to the side. Now solve this for x. Get the x by itself on one side. Oh, no, not square root. The x is being multiplied by the root 2. Yes. Thinking. Yeah, nice job. You get something? So if you took that times the square root of 2, would you get 12? Perfect.
So then would this whole thing be that, or would it just be 6?
No, it would be both of those together.
Okay.
8 times the square root of 2, would that equal 12? What's the exact value?
I don't know, but 8.485 12.005. So I just started, but I just rounded to the nearest.
Oh, decimals. What's the exact value? All right, so normally, here's one way we can think about this. Typically, if I have the short leg, or those are both the same, right? This is a 45, 45, 90. So I know x and y are the same. If I figure one of them out, I'm going to figure both of them out. So that's nice and easy. It means I only have one calculation for this problem. Now, normally, if I knew that leg length, what operation would I have to do to that x in order to get this hypotenuse? What do we normally do? Multiply it by root 2, right? Normally, I would take x, I'd multiply it by the square root of 2, and I would get the hypotenuse, which is a 12 in this case. So if you look at that, we actually have like a little mini equation. Well, whatever x is, if I multiply it by the square root of 2, I know that it needs to equal 12. So that's just a little mini equation that we can set up. Now, let's just solve this little mini equation for x. Like if it's being multiplied by the square root of 2, how do I solve for x? What do I have to do to both sides? Divide. Yeah. So let's divide by the square root of 2 on both sides. And we see that x has to equal 12 over the square root of 2. That's awesome. Except for one thing. We can't leave radicals in our denominators. We learned that several units ago in our rational unit. So how do I get rid of a root when it's in the bottom of a fraction? Yeah, what do we multiply by? Multiply it by that exact same radical on the top and bottom. So I'm going to multiply this by root 2 over root 2. Because when I do that, I get 12 root 2 up top. There's no real calculation there. But the nice thing is, what happens in the denominator? What's the square root of 2 times another square root of 2? It's just a 2, right? The roots cancel out and leave me with a 2. And right now, in green there on the right, I no longer have a radical in the denominator, which is great. That's what we want. That means that we've got, or we've rationalized the denominator. But if I wanted to simplify it all the way, I've got a 12 up top and a 2 on bottom. What is 12 divided by 2, everybody? It's 6. So I can actually write my final answer here as 6 square root of 2. I know. I'm going to give you some shortcuts, don't worry. But if you totally blank out on everything, this is the most like basic direct way to get to that answer using basic algebra. So this side is 6 root 2. And now just to test it, is this correct? Well, if this is 6 root 2, to get that hypotenuse, what would I need to multiply that by? Another root 2. And so let's see, does that work? Is 6 root 2 times another root 2 equal to 12? Well, yeah, because root 2 times root 2 is just 2. And 6 times 2 is 12. So that works. So did some of you just think about it backwards like that? Like what number times a root 2 would be 2? And here's the way that I like to keep this all straight. My own shortcuts that my brain comes up with. We know that this is shorter. If we're going from a short leg to a long leg, we multiply. Right? To go from something smaller to bigger, you multiply. Well, if you're going backwards, we don't multiply. If we're going from a bigger number to a smaller number, what operation would we use? We'd use division. So if I'm going from the bigger side to the smaller side, I'm going to use division instead. The neat thing is, we still would use that same radical of root 2. Normally, I would multiply by a root 2 if I'm going from the small side to a bigger side. But here, if I'm going from a bigger side to a smaller side, I'm going to divide by a root 2. And so I can just say, hey, well, then that's going to be 12 divided by root 2. Then just rationalize your denominator, multiplying it by root 2 on top and bottom. And then that will simplify to the 6 root 2. That's how I like to think about those. Normally, you'd multiply by root 2, or if it's 30, 60, 90, you multiply by a root 3. But if you have the long leg, just divide by a root 3 to get the short leg. I think that's it for today. Great, we have half an hour to practice. Grab out your Chromebooks, everybody, and let's do some delta. Yes.
Technically, at that point, now that I think of it, can't you just like take whatever number is there, so like say 15, divide it by 2, and then add a root of 2 on the end?
Yeah, I mean, if we're now doing 2, just take 12, divide it by 2, get 6, and put a root 2 after it. Sometimes it won't be divisible by 2, though. Yeah, if it were... Yeah, we can do some other scenarios here. Like if this is a 1, what would x be? So we had to take that number, divide it by 2, and then just put a root 2 after it. but up top. So this would actually be just root 2 over 2. Or if it were something like 13, well, it'd just be 13 over 2 root 2. Just put the root 2 next to it and then divide it by 2. And if it were a 30, 60, 90, it is. So watch this. Let's take that short leg. And if this is, let's say, 30, what would x be? Yeah, x is 10 root 3, right? You divide it by 3, and then you multiply by root 3. Essentially, that's your most expedient shortcut. And then once you have this, then what would y equal? The hypotenuse is going to be what? Remember, to go from the short leg to the hypotenuse, you just multiply it by 2. So you only multiply the coefficient. That root 3 would still be there hanging out. How about that? What's x? It's a lot easier than you think. Mm-mm. Yeah, right? Because isn't this side just the x times root 3? So if there is a root 3 already, well, its coefficient is going to be x. Just 6. Because then that side would be 6 root 3. So it's really nice if you already have a root 3 by that side. The others are going to be a piece of cake. And then the other thing you might see is if you've got something like, if you have a radical already, like a root 6. So
9, so it'd be 3 times the root of 2 over 3, which is 3 times the root of 2.
what do you think it is?
3 times the root of 2.
It's actually just going to be a root 2. Because 6 is root 2 times root 3. And so you're really thinking about, to get this leg, what's in front of the root 3 essentially? Because whatever this is, I multiply it by root 3 to get this side. So if that's a root 2, when I multiply by root 3, I'd get a root 6. And so like if you do work backwards, how do you figure that out? Well, you would just divide by root 3, right? Normally you multiply to go bigger, you divide to get smaller. If you're dividing radicals, if it's the same index, square root, you can just divide the numbers inside. 6 divided by 3 is 2, and that's your root 2. All kinds of fun we can have with this. Yeah, questions? Delta math's not working? Dun, dun, dun. For 3 years. Did you try refreshing the page? No, it usually remembers it. It'll give you credit for it too and just like give you the next one. Did you try it?